Hi everyone. So last time we understood that the question of depth in learning, like we need depth, is strongly related to the question of needing nonlinear discriminators or nonlinear functions that represent the function we are trying to learn. Right? So this time, this whole video is about a simple example that we call the Xor example. That will explain. It's a concrete example that will show us how nonlinearity can be useful. So let's say we have two variables. These variables are binary, meaning they can only be 0 or 1. We'll call them x1 and x2. And then we have the XOR function. This is the function we try to learn. And basically x1 XOR x2 equals to 0 if x1 equal x2 and equal to 1 if x1 is not equal to x2. So if you have 1 0 or 0 1, the output is 1. If you have 0 0 or 1 1, the output is 0. So as you see from the figure here is that we cannot have a linear discriminator that learns this function. So if we want to learn between the two classes, right? So we want a classifier that given the input will tell me whether the output should be 1 or 0. This discriminator cannot be linear in that space, right? In the two-dimensional space of x1 and x2, because I cannot draw one line that will put all the zeros on one, all the O's in this figure on one side and the X's on the other side, right? I have to have a non-linear decision boundary. So we will call the vector x basically the vector of x1 and x2, and the cost function that we will consider is the mean square error cost function, and in this case mean square error meaning mean over all the possibilities, and here the alphabet or all the possibilities for the values of x are 4 possibilities. That's why we divide by 4, and then we take the square of the error. The error is the difference between the predicted label and the true label. We take the square of this, we sum over all possibilities, and then we divide by the number of possibilities, which is 4. Now assume we want to only use linear functions within the model. So here we are trying to make the fact that there is no line that can distinguish between the x's and the o's, we were trying to make it more concrete or more rigorous. So let's say I want to distinguish between the two classes through a linear decision boundary. So the parameters of the model will consist by a weight parameter that gets multiplied by x1, a weight parameter w2 that gets multiplied by x2, and the bias parameter b. So f of x and theta, which is f of x and w1, w2, and b equals w1 x1 plus w2 x2 plus b. And the j corresponding to theta, so the cost function corresponding to a model with parameters theta, is equal to 1 over 4, and then corresponding to 0 0, f star of 0 0 equal to 0, right? So f star is the true label of 0 0, x1 equal x2, so the output should be 0. So f star of 0 0 equals 0. F of 0 0 equals b. If I square that, I get b squared. Now corresponding to 1 0, f of 1 0 equals w1 plus b. And f star of 1 0 equals 1. So f minus f star square equals w1 plus b minus 1 squared. Corresponding to 0 1, I get w2 plus b minus 1 squared. Corresponding to 1 1, I get w1 plus w2 plus b squared. Because f star of 1 1 equals 0 and f of 1 1 equals w1 plus w2 plus b. Now if I were to choose w1, w2 and b to minimize that cost function, then the answer, the optimal solution, will have w1 star equals 0, w2 star equals 0, and then we will end up by having 1 over 4 2 times b minus 1 squared plus 2b squared. So basically we will end up minimizing b minimizing b minus 1 squared plus b squared, the choice of b that minimizes this, and the choice of b that will minimize this is the b that's perfectly in the middle between 0 and 1. So that you have b square equal half square, and b minus 1 square is half square as well. So B ends up being half. Now, if we draw this decision boundary, then it looks like this, right? Now, this decision boundary makes mistakes at half the points, right? So if I say, for example, that to the right of it I'll classify as 1, to the left of it I'll classify as 0, then it will make a mistake in half the possibilities or in half the examples, right? Because there is a cross on the right and there is a cross on the left. There is a circle on the right and there is a circle on the left. So this is as good as random guessing, meaning that if my classifier is as dumb as a random guessing classifier that just takes with probability half and half, classifies each point either as 1 or 0, it will do the same performance. So that means that linear decision boundaries are catastrophic in this example. Like, they cannot do any better than random guessing, because the optimal linear decision boundary gives you a performance that's the same as random guessing. Now consider the following solution with a non-linear decision boundary that has what's called rectified linear unit or Relu activation functions. And we'll see as we go through the example what exactly is a Relu activation function. So we'll start from the solution, right? And we'll see what the solution represents. So we have x1 and x2. Then we have two intermediary solutions, which are represented by, well, the first is represented by x1 w11 plus x2 w12 plus c1. So it has two weights and a bias. The second is represented by the x1 times w21 plus x2 times w22 plus c2. And then the output of these intermediary solutions is followed by Relu activation functions, and then the output of the Relu activation function is multiplied. The first one is multiplied by w1 and the second one is multiplied by w2, and then they are added together. Okay, so here they are added together for the final solution. Right? So let's see what choices for W are considered for this solution. So W is the matrix consisting of W11, W12, W21, and W22. And this matrix is all ones in the solution we are considering. Okay? So this is 1, this is 1, this is 1, this is 1. Now C, which are the biases for the intermediate solution, equals 0, negative 1. Meaning that C1 equals 0 and C2 equal negative 1. W, which are the weights in the second stage, are equal 1, negative 2. Meaning that W1 equal 1 and W2 equal negative 2. Now the X, which are all the possibilities for X1 and X2, can be represented as a matrix of 0, 0, the first possibility, second possibility 0, 1, third possibility 1, 0, fourth possibility 1, 1. Right? So X is the data. Right? So this is the matrix representing the data vectors, and these are called features. Right? These two columns. So the first is the first feature, the second is the second feature. Now when I have the data, so x1 is the first feature, x2 is the second feature. If I have my data vector, transform it by the first linear transformation through w11, w12, w21, and w22. If I multiply these matrices, I get these columns, 0, 0, 1, 1, 1, 1, 2, 2. Right? Because what's happening is that both these neurons, since all the weights are 1s, are adding x1 and x2. So for the first vector, you get 0. For the second vector, you get 1. For the third, you get 1. For the fourth, you get 2. Now, if I add C, right? So C1 equals 0, C2 equals negative 1. So if I add C, I end up with 0 as is, 0, negative 1, negative 1. 1 as is, 1, negative 1, I get 0. 1 as is, 1, negative 1, I get 0. 2, negative 1, I get 1. So I get this matrix of 4 vectors. Now, this represents the output of the hidden layer before activation. And how it looks like? It looks like this. 0, -1 is this point. 1, 0 is this point. Another 1, 0 is again another point. And 2, 1 is this point. Now remember that the first and fourth points belong to the same class. We mark them with crosses. The second and third points belong to the same class. We mark them as circles. Now here again, I cannot distinguish between these points through a linear decision boundary. Actually, all the points lie on a single line. The only way I can do this, or one way of doing this, is if I use the Relu activation. Relu is basically an element by element maximizer of the value of the feature and 0. So basically, it pushes all the negative features into becoming 0. And what happens here is that these 2 points will remain intact, this point will remain intact, but this point will go to the origin. Because this point is 0, -1, it will become 0, 0, right? So Relu will move this point to the origin. Now after we move this point to the origin, now we can draw a decision boundary, right? So after this point becomes here, I can have a decision boundary that's linear and distinguishes between the circles and crosses, right? And the way that it happens is as follows. If I have this W, which is the weights in the last layer, right? So these weights, if I have them equal to 1, -2, then I multiply that matrix 0, 0, 1, 0, 1, 0, 2, 1, which is the output of the hidden layer after activation, right? So after adding C to this vector, right? After Relu activation of this vector, the -1 becomes 0. So I get this vector. Now when I multiply it by W, I get 0, 1, 1, 0. 0 is the F star value of 0, 0. 1 is the F star value of 0, 1. 1 is the F star value of 1, 0. And 0 is the F star value of 1, 1. That means what? That means that the mean square error, or the MSE, will equal 0 because F of X is identical to F star of X. The predicted label is the true label, right? So that example showed us what? Showed us that only linear transformations failed completely at this task, right? They didn't do any better than random guessing. And when we added the possibility of Relu activation functions or rectified linear units, now we'll come back to that later in more detail and why are they called rectified linear unit and analyze their properties. But when we added this nonlinear activation, now depth became useful. So now we can have 2 layers that are doing different functions. And through these 2 layers, we can perfectly accomplish, or we can definitely achieve this XOR or learn this XOR function. Thank you.